ShArc is a precision geometric measurement technique for creating multi-bend shape sensors. These devices are designed to detect curvature in the XY plane. Most bend sensors report only a single number, which is a gross measurement of overall flexure. In contrast, ShArc sensors can provide detailed shape, even when there is more than one bend along the sensor. ShArc sensors detect curvature at many points, building a model of the shape from a series of connected circular arcs. This particular prototype creates models using 8 arc segments, but the technique easily scales to using many more arcs. ShArc sensors are extremely low cost, highly responsive, precision measurement instruments. Most bend sensors detect bending by measuring strain in some material. In contrast, ShArc sensors directly measure changes in geometry and are more like digital calipers. Here, we show the accuracy of our prototype sensor. The graph shows both the live data from the device as well as the known geometry of a 3D printed form. When we shape the sensor onto the form, you can see how well the measured data corresponds. Even the unintentional small gap at the end is well modeled. ShArc sensors are built using 2 flexible strips that are held a constant distance apart. In our prototype, there are transmit and receive strips that each contain a series of carefully designed electrodes. The spacing between the transmit and receive strips is set by a series of spacer strips. A small clamp on one end binds the stack, and an elastic sleeve keeps the strips aligned and pressed together. A circuit board measures the capacitance between the electrodes on the transmit and receive strips. ShArc sensors work by measuring relative shift-to-fit arcs. Imagine 2 measuring tapes held a fixed distance apart and joined on one end. If this unit is held flat, the measurement marks on the 2 tapes will align. But if the unit is formed into a circular arc, the inner strip will have a smaller radius than the outer strip. Assuming the 0 points are constrained to a line, the other marks will drift apart. The tighter the curve, the more the 2 sets of markings will diverge. This is similar to what happens when a paper book is bent. The binding keeps one side of the pages aligned, but the other side fans out. Our prototype measures shift via changes in differential capacitance. The bottom strip contains a series of transmit electrodes. The top strip has corresponding pairs of receive electrodes. As the transmit electrode shifts relative to the receive pair, the circuit becomes unbalanced, creating larger capacitance to one side or the other. Measuring this differential capacitance reveals the degree of shift. Our prototype has 8 measurement pairs. When flat, all are aligned, giving 0 differential capacitance. But as the sensor is curved, the transmit and receive strips progressively misalign. By measuring the shift over each segment, we find its radius of curvature. Because the total shift to any measurement point is the sum of the shifts in all of the segments, the total curvature to any point can be found irrespective of any subsegments. This gives ShArc sensors a unique tolerance to measurement errors. Unlike jointed systems with encoders, angular errors do not accumulate with each measurement point. We prototyped a number of sample applications for our sensor. Our first demo uses the sensor to detect the shape of a bent finger, as might be used in a virtual reality glove. Because the shape is modeled by many arcs, there is no need to make presumptions about the location of finger joints, as is required with less capable sensors. Given the precision of the device, it is ideal for measuring complex curves on objects. Shapes of real objects can easily be entered into CAD or other drawing packages. We created a long version of our sensor to detect curvature of the spine. This is useful for providing real-time feedback and long-term monitoring of posture. This also suggests many applications in physical and rehabilitation therapy. Everywhere we look, we see things that bend. ShArc sensors provide a precise and cost-effective way of understanding the shape of our world.